you very much. So this is talk that's inspired by sort of two things I've been doing. One is writing a paper about the history, about sort of some aspects of history of programming, and the other is I recently started at the University of Kent as a lecturer, which is, I think, British way of saying just a sort of entry-level academic, whatever you call it. And one of the things that I've been teaching over the last year is software engineering. And I think this is one of the courses that very many universities teach very badly. So some of the ideas in the talk will be sort of inspired by my attempts to do this better. So I use this sort of title, fundamental principle, in the talk. So what do I mean by this? I think we really what I mean by this is the sort of knowledge that will actually remain relevant in 100 years, or maybe just 50 years would be fine. If you look at sort of some branches of physics, then there's ideas that exist since 17th century, and many of those you can still find useful ideas there. They might not be sort of exactly what modern scientists use. We don't use sort of we have theory of relativity, which is making things sort of more refined and handling cases that previous theories didn't, but still there's actually a lot of knowledge in science from 17th century that's still somewhat relevant, and we teach it to school children. I think this is very related to this idea of what we should teach at university, and I do think that universities sort of should primarily be teaching things that are the sort of fundamental pieces of knowledge, and then have some sort of applied practical side where people get the opportunity to learn the things that they might find useful when they work somewhere. But the sort of fundamental question is what are the things about software engineering that if I write a book about it and you buy it in 100 years, it's still going to teach you something useful. It's basically a way to get really rich. And so in computer science, if you look at the more mathematical side of computer science, we have things like this. So the halting problem says it's impossible to give a program that if you give it some other program, it will decide whether the other program will terminate or not. So that's the sort of fundamental undecidability theorem, and this comes from 1930s, and it's something that's still true. It's still important. It still limits what kind of algorithms we can write or define, and it's going to be true for the next until the universe ends. So that was what we have in sort of theoretical computer science. If you look at what typical software engineering course at university teaches, it might teach Agile or Scrum if you're lucky. If not, then it will teach you Waterfall. It might teach you UML or some sort of domain-driven design methods. It will teach you object-oriented design principles, and if you're lucky, they will tell you about sort of continuous integration tools like Docker, Kubernetes. Which of these things will still be useful in 100 years? I think none. UML, well, I'll say more. But of course, Lisp will be. But that's so. I think what the kind of questions that we need to be sort of looking for is Are there some sort of fundamental constraints on what kind of systems are actually possible to build? Or are there some sort of laws or truths that are fairly general about the sort of guaranteed costs and correctness of systems that we're building? And when you look at these questions, then you're sort of quickly realize that this is not really the same kind of problem as, say, the halting problem, because it's not really a formal mathematical thing. And if you make it a formal mathematical thing, then you lose the most important aspect of it, which is that all these things actually involve sort of humans and the environment in which all those systems run. So can we say anything that's sort of fundamental or certain about these? And the proposal that I'm sort of making here is that the things that will remain relevant and useful knowledge and true knowledge about software engineering are really things that are sort of aware of the history of those ideas and are doing some sort of critical analysis of the various software development tools and practices of the past or present. So I don't think anybody should be teaching UML or waterfall or agile, but we should be sort of trying to explain the history behind these ideas, the context that led to them, and the sort of reasoning in which they were created. And I'll try to go through a couple of interesting ideas from the history that have this sort of critical reflection of some idea or some tool or some method that's sort of aware of the historical context. And I think some of these are actually sort of as close as you can get to fundamental principles about software engineering. I'll have a lot of history in this talk, and I think here it's not just because I like history and because I want to sort of tell you something about history. I think it's because that's really a necessary component of looking at those software engineering ideas. So if I told you just the bits in the talk without the history, it wouldn't be doing what it was supposed to be doing. So this is really sort of trying to integrate that history with the technical aspects. And the first bit of history here is what was programming like in the 1950s. So this is John Bacchus' quote, who created Fortran, and he was saying, programming in the 50s was black art, a private arcane matter, and each problem required a unique beginning at square one, and the success of program depended primarily on programmers' private techniques and inventions. So you really had this, what I would call hacker culture of programming, where it was very reliant on the individuals, and every individual had their own craft and style that wasn't really widely shared. And in that context, what happened was that especially people in sort of management positions, both in businesses and in the army, which was heavy user of computers, they created this NATO or organized NATO conference on software engineering, and this is actually the first time the term software engineering was used in the sort of meaning we use today. So this was not just some random conference on software engineering like many other conferences of software engineering. This was an event that actually defined the phrase, and the motivation for the conference was to sort of transition programming from a craft for long-haired priesthood to a real engineering discipline. I don't know what's wrong with long hairs, but apparently they didn't like it. And this is sort of, if you read something about history of software engineering, many people will say this is when the sort of transition really started. But there's actually some more fine-grained, refined views which point out that so this was 1968, and the next year, the 1968 conference, everybody was excited about this idea. They sort of saw the problem with the hacker culture and wanted something better. And there was general agreement that this is a problem that needs to be addressed. In 1969, 1 year later, they created another conference which was trying to actually come up with concrete software engineering methods. And this is widely regarded as a failure where nobody could agree on anything with anyone else in the room. There were sort of two main, I think, cultures there. One was the sort of more academic, formal approach where people said, well, you have to treat programming like a mathematical discipline where you prove things about programs and then you compose correct things into correct systems. The other was the very sort of managerial culture where people were really more looking for ways of sort of controlling the production as you do in a factory by having workers who are easily replaceable, and their main concern was that these programmers were just sort of, there was too much reliance on those individuals' sort of arcane skills. So I think what might be interesting here is also the sort of cultural divide between more formal world and the more business world. I think in many ways that's something we're still facing these days. When you go to a job interview and they ask you, okay, give me the complexity of quicksort, that's asking the sort of mathematical question for someone who's going to be mostly working in the other culture. But one of the outcomes of this was this approach to sort of apply industrial methods of production to software, and find ways of building software where you have control over budgets, scheduling, and most importantly, the workforce. And a lot of this was this sort of attempt to eliminate this reliance on individual where you have to hire a programmer, and if they were good, they would do the thing you needed a lot faster than if they were bad. So it was sort of an organizational attempt to solve this problem. And I think one interesting point is that if you're aware of this historical context, then a heavyweight software process methodologies like the waterfall is actually something that makes relatively good sense. Like the sort of historical context quite naturally leads to this idea that you need to have a very structured process for how you build software. And I think one sort of fundamental software engineering idea is sort of, if you understand that context, then follow the reasoning that led to these heavyweight methodologies. That doesn't necessarily mean everybody should learn details of a waterfall management process, but it's useful to actually know that this was an idea that appeared in a certain historical context and was solving certain kinds of problems. And if we ever get to a position where we have similar sort of context, we might be able to learn from this. So what followed, this is Christiane Floyd, and she wrote a paper in, I think the first draft was 87, but you can get a copy that was published around 90s, which is basically Agile 13 years earlier. So she's saying there's these sort of two paradigms of software engineering. One is this product-oriented idea, which is what I was describing, where you see software as a product serving some fixed use case. And then she describes this minority view that's process-oriented, where she says that software emerges from the totality of interconnected processes of learning and communication in evolving environment. So this is just a sort of nicer way of summarizing the Agile Manifesto, right? It's sort of less phrase-based, so it's sort of hard to remember, but the ideas are pretty much there, where she's sort of describing these process-oriented methods where people really sort of focus on the communication with the customer, and the whole process is the sort of teams learning what the system needs to be like and understanding the changes of requirements. So this was something that was already around at the end of 80s, and then the sort of logical, or the thing that followed from it was the sort of more agile methodologies or extreme programming and things like that. And I think this is something that's really useful to understand, because the context here is really important, and it was also partly sort of pushback against this managerial culture where we were trying to eliminate these unreliable programmers from the sort of process and make sure that doesn't matter. I think this is more sort of acknowledging the individual's contribution to the world. And I think you can say the same. You can sort of treat many other things in the same way, where if you look at something like agile, something like UML, it's useful thing. It might be a useful thing to know, but you can actually learn a lot more about it if you see it in the sort of historical context, where some of the early users really tried to sort of have this: we will fully specify a system up front and have a control over the process. And UML, I guess, underwent a sort of interesting development where it became more of a communication tool than a tool for sort of fully describing things up front. There are also a couple of things in the past where sort of people have already done the critical reflection that I'm advocating for. One really nice example is the IBM operating system 360, which IBM was creating as a sort of way of unifying their operating system for a range of different machines they were building. And this was massively delayed, partly because it had a lot of conflicting requirements that often were changing as their sort of plans were adapting in the company. Partly it was also just really hard thing to build. So it was sort of, as it sometimes happens in the history, it was like one of those things that are just more complex than anything we've ever done before, so we really don't know. And there was quite a lot of reflections on how that failed or how that didn't work. So Fred Brooks wrote a famous essay, No Silver Bullet, and that's a part of the Mythical Man Month book later on, where he sort of trying to understand what's the source of all this complexity in those systems. And he's saying much of complexity that a software engineer must master is arbitrary complexity forced without rhyme or reason by the many human institutions and systems to which his interfaces must conform. So this is really sort of getting to the core of why software engineering is so complex, and I think it's also really clearly saying why. What's the difference between an algorithm and a software system? Because if you talk about algorithms, there's no human institutions involved in quicksort. But if you talk about a system to calculate taxes, then suddenly a government becomes a part of your components in your system because they will change the laws. So Fred Brooks sort of distinguishes between this essential complexity, which is really the complexity that's that's resulting from the kind of thing you're writing. Like if you're writing a system that will calculate taxes, then this is all the tax laws, and the specification of those aspects of the system is just as complex as any program that can implement it. Like, there's no way of making that simpler unless you lobby governments to make the taxes simpler. And then there's accidental complexity, which is all that sort of results from our imperfect tools. So the fact that you're using C# rather than F#, that's just accidental complexity. But one of the sort of key points that Fred Brooks makes is that, and I think I have a nice summary quote from him here. He says, "There's no single development in technology or management which by itself promises an order of magnitude improvement within a decade in productivity, reliability, and simplicity." And this is not just sort of some random quote that sounds clever. This is actually based on sort of his analysis of this accidental and essential complexity, because he says, well, the essential complexity, that's something you can't reduce. The accidental you can, and if you make your languages 10 times better, like, I don't know, I'm not going to suggest anything, then you're reducing this half to a 10th, but overall, the whole thing was still reduced not even to a half. So this idea, I think, is really sort of based on some understanding about fundamental principles, where we just can't make programming 10 times easier by making languages better. The other case in history where there was really an amazing detailed discussion about it was various attempts in the US to build a system that would shoot down nuclear missiles sort of from the Soviet Union targeting the States. And there was a long history of this, but in the 80s, there was a Star Wars project which was trying to build a fully automated system to do this. And a lot of people got involved in the debate whether you can actually build a reliable system to do this. And one of the comments here was, again, looking at why are digital systems so hard to build. And this is Dave Parnas' paper, and I'll have a references at the end, where he says there's sort of three levels of complexity. One is analog systems, where they have this sort of nice property where small change in the input results in a small change of the output. So you just have to have some amount of you operate on ranges, and if the ranges are large enough, you have the sort of, you can make safe estimates. And this was true for some analog computing devices sort of before the age of digital. There's digital systems which don't have this property, where sort of in a digital system you can write things so that a small change results in a big change in the output. But fortunately, we can still build hardware has gotten quite reliable. I'm amazed that my CPU still works perfectly fine. But that's largely because they're built from lots of repeated components. So you can sort of fully understand the states in a component, and then you repeat the same thing, and that's something you can still fully understand. But the problem with software is that they're digital and they don't have this repetition. So you have lots of components where small change in input can have a large effect on the output, but there's no way to understand to reduce this complexity. You just have lots of states, and you have no way of reducing the complexity to something understandable. You just have to understand the whole thing. So this is one of the sources of the complexity, or this is the sort of primary reason why the kind of systems that we're building are really different thing than anything else that's been done. And this was one of the reasons why building the Star Wars computing systems would why it's not something that you can just sort of give to a subcontractor and they'll do it reliably. It's really building something of a different level of complexity, and an analysis from Licklider was complex software can only be mastered if it's developed progressively with the aid of extensive testing and then operated more or less continually in a forgiving environment. So this was, I think this was largely based on him sort of talking to people who did software and learning about all the failures that they've experienced and sort of analyzing what were the different cases where things went wrong. But there's like a huge number of constraints in this quote that says what's actually possible to build and how. And he was using this to argue that you can't actually build the defense system. And a great book that documents this whole story is called Arguments That Count. But so the 2 points here would be, first of all, the defense would not be reliable because we have no spare planets on which we can fight trial nuclear wars. And so testing the anti-ballistic missile system is impossible. You can't have realistic testing because you just can't sort of simulate the environment that's going to be happening when your system is in production. The other point was that the enemy has it easier, and building very, very expensive defenses would actually just motivate the Soviet Union to build relatively cheap improvements to their offensive missiles, which would circumvent those defenses. So this is the case where not only the environment isn't forgiving, but it's actually actively working against your system, and you just can't improve the system sort of faster than how the environment changes. So I think these two are, again, really nice sort of applications of some fairly fundamental software engineering principles to argue that these things cannot really reliably be built. But one important point here is that those are sort of compared to like a mathematical formal statement about a halting problem. These are relatively sort of weak principles. So it's true that the US eventually developed this project into the Patriot system for shooting down missiles. Can it be reliably built? Well, when they put it in production, it first accidentally hit a British fighter plane, killing 2 people, rather than shooting down missiles. And when it was used in the Gulf War, they had to update the software nine times during the sort of several months of the war. So I think that's really just proving the point about sort of not being able to test it reliably, which is the first thing, and having to sort of build these things gradually. So I think this is one example where it's sort of significant enough that people have done serious research into the history, and the book I mentioned has really great documentation of sort of what were the principles that people discovered while looking at this case. And I think there's actually quite a lot we can learn from these even today, even when you're not building missiles, because at the panel last night we decided that we shouldn't do unethical things. But if you're doing ethical things, you should still be aware of these constraints. All right, so that was looking at some sort of concrete ideas, and I've covered 2 areas. One is basically things that we know from, or one is looking at sort of concrete historical case studies like the OS360 or the ABM systems. The other was looking at some of the sort of more traditional things that we teach, like methodologies and modeling, and sort of trying to convince you that we should add that historical perspective to it. The other thing I want to get back to is this idea of sort of calling this thing software engineering in the first place, because really the sort of term software engineering is something that appeared at the end of 60s, primarily as a managerial response to some perceived crisis of how programming is done. So this is something that's not given, and we probably, I don't think we'll change, we'll sort of stop talking about software engineering, but it was a metaphor that people sort of started using for finding one particular response to a problem that they had. And every metaphor has fits and misfits, so there's many things where software engineering isn't really like engineering. And that's not necessarily our fault. I think that's more of a sort of fault of using a metaphor that might not always be appropriate. And there are many other metaphors. So lots of people look to architecture or urban planning for ideas about how to deal with complexity. Design patterns are a nice example where that's actually something that came from architecture, although I'm told that what we did to design patterns is something that the architects wouldn't really appreciate. But there's other metaphors, like thinking about programming as writing, and I think you should stay in this room if you want to hear more about the idea that sort of are programming languages. That's really sort of in this space of are we talking and writing when we program. Or there's a sort of idea that we should think about programming more as growing a system and sort of treat it more as a gardening process. And those are all sort of interesting alternative ideas for thinking about programming or whatever it is that we actually do. Why do these metaphors matter? I think it's sort of very nice to say programming is like writing, or I think Grace Hopper famously had an interview in, I think, Cosmopolitan at some point where it was sort of interview that she did to convince more people to get into programming, where she was saying, well, programming is a perfect job for a lady because it's just like planning a dinner. The sort of interesting point here is you can make all these analogies, but why does it actually matter? Why are we actually doing it? And I think the really interesting aspect here is that those sort of metaphors, those sort of ways of looking at programming, they sort of change how we think about the problem, and they also shift our emphasis. So if you talk about writing, then really you're focusing more on the sort of communication aspect of programming. If you're talking about growing, then you're really focusing on the sort of development and the gradual development and long-term viability and maintainability. The one metaphor I want to sort of look into a little bit more, because I think this is another sort of, aside from sort of looking at concrete historical cases and looking at practices in context, I think those sort of metaphors are another really useful way of importing clever ideas and possibly fundamental ideas into how we talk about software. And there's a great book by Jane Jacobs about urban planning, which looks at the kind of it looks at it's just a massive rant against modernistic planning of the 50s. But one of the points that she's making is that cities have certain kind of complexity, And I think what's really fascinating about this is that there's very similar sort of structure to this complexity that we have in programming. So I told you earlier about the sort of complexity about software systems, where you have analog systems, digital systems with repetition, and digital systems that are not repetitive. In architecture or urban planning, you have problems of simplicity, which is the kind of problem where you can understand all factors in isolation, and then you have full understanding of the problem. Then there's problems of unorganized complexity, which are the problems where you can apply statistical methods and statistical analysis to actually reduce the complex thing into something tractable. And then cities are a case of unorganized, of organized complexity. And problems of organized complexity are the kinds where you actually have to look at you have to look at the problem in a sort of full richness of it. You can't just easily take an average, because that will actually remove all the interesting aspects of it. So in cities, there's lots of complicated processes, and all these city processes are different. They're all very complex, and you can't sort of easily abstract away and treat them as something simple. So what she's arguing for in this book is that when you're trying to make sense of a city, you really have to look at some of the concrete processes in detail. And you have no chance of understanding all the processes in all the details, because there's just too many of them, but at least you'll get some sense about some concrete aspect of it. And the other point that she's making is that one unaveraged value tells us more than a statistic. And I think that the concrete example here is if you have a bookshop, that's a chain of bookshops, which has branches in different parts of the city, and almost everywhere in the city they're open until 10 p.m., then there's one branch somewhere that closes at 5. That gives you a really good indication that that part of the city works differently, presumably because it's sort of area with offices where nobody stays in the evening. So it's sort of very much arguing for not trying to simplify and treat the sort of whole thing at once as something reduced, but look for all these sort of detailed aspects that you then study in their full richness. And I think there's a sort of useful analogy here with software engineering as well, where nobody really gives you a full specification of what the city will work like, because that's just silly. The other bit from architecture and urban planning that I think is really interesting and relevant to our business here is building. In architecture, there's a debate about how, or there's a book called How Buildings Learn, which looks at sort of what happens to buildings once they're built over. I think it's written in the US, so it's like what happens to the building once it's built in the next 20 years. But he does have some European examples with like 500 years history as well. And the sort of interesting point is that, and again, I'm picking this because I think it's very relevant to software. So when I read it, just replace building with software, and you'll see what you get. So none of the buildings are really sort of designed to evolve. That's you sort of build a building to be a pretty amazing piece of architecture, but what happens to it in 50 years, that's just a completely different process. And the book has lots of good ideas about how to make this better. So one point is that different aspects of the buildings evolve at different speeds. So the sort of core structure will be the most stable bit, the engineering networks, and when you figure out that you suddenly need to install internet everywhere, that's something that changes more often. The other point is, how do we actually sort of change the building process to teach maintenance? So one idea in the book is that you should always build a building so that some bits of it will need replacement after a year, because that's sort of early on teaching the owners of the building and sort of getting them ready for the real thing that will happen in the sort of next 100 years of using the building. And another great idea is about choosing material. So the book is very much in favor of using traditional materials where you understand how they behave. And especially there's this great idea that you should see that something is getting bad before it actually breaks. So if you sort of have some metal cladding over your building, then you don't see what's happening underneath. And if it starts rotting, then just one day the whole thing will fall down. If you're using wood, then you just look at it every day as you walk past and you see, well, it's still okay, it's still okay. And you sort of see the material degrading. So I think this is something that we might want to think about in the context of software as well, where very often sort of you don't see how your systems are gradually degrading over time. All right, so to summarize, I want to say, I think, two things. One is that I think it's very unfortunate that we call this thing software engineering, because that's really just one particular take on it. And I really believe that we sort of have to look at the full historical context to understand what we're doing. And I think some useful structures for understanding this might be to look at the different cultures involved. So there's the sort of hacker culture of the 50s that I was talking about, which then inspired partly the sort of more managerial approach to software, the more mathematical approach to software, and I think the sort of move to the process-oriented or more agile methods, that's something that really sort of emphasizes the engineer as a human part of it aspect. So I think the foundations really can't be just looking at one of these cultures. Like, you can't give a mathematical theorem which will be a foundational truth about software engineering. I think what we need to be doing is to sort of look at the history and understand the context for all these ideas, because very often the fundamental idea isn't the idea itself, but the sort of mental process or the thought process that happened when, in a certain context, we are trying to solve certain problems and we come up with certain ideas. So I think this sort of complex is what is really a fundamental idea. And since we are in France, I'm allowed to have a philosopher in the talk, which is great. So Bruno Latour has this great book, We Have Never Been Modern, where he basically says what I was just saying. He says, and he's talking about sort of sciences in the social context more generally. He says we must rework our thinking, or he doesn't actually say this, it's sort of summary of the book. But the summary is, we must rework our thinking to conceive of a parliament of things where natural and social phenomena and the discourse about them are not seen as separate objects, but as hybrids made by the interaction of people, things, and concepts. And I think that's really the sort of this parliament of things. This is where our fundamental software engineering principles will be found. So to summarize, we need more history, not just because history is fun, but because history is actually inherently important part of software. We need to look at this interaction between different kind of cultures that contribute to the world, and that's where our fundamental knowledge about software engineering can be found. Thank you.